In this lecture, we're going to look at a complete but very simple program and also make a few comments about style and JavaScript and some of the issues that make JavaScript different from the languages you may be more familiar with. Uh, One of the things that you'll notice throughout this discussion and later ones is there are very many different ways that we could organize our code and do things in JavaScript, and I'm picking one and I'll try and be consistent with it throughout the course. You may find, especially if you have more experience, to be comfortable with some other way of organizing your code. But let's just stick with mine and for now. We're going to do a very, very simple example. We're going to draw a single triangle, and on one hand you can say it's a pretty trivial application. On the other, though, it'll consist of almost all of the parts that are going to be repeated in every application you do, no matter how simple or how complex. Now, first decision I've decided on in this is to always use at least two files. Minimally, there'll always be an HTML file, and we'll execute the program by just executing that HTML file, usually by just clicking on its URL within the browser, and that file will wind up calling a JavaScript file that has the same name but not the same extension. The difference will be that the HTML file will describe the page itself. I mean, that's really what HTML, the hypertext markup language, is about, is how do we describe web pages. So it'll describe that page, its size, the resources that it needs, and it'll also include the shaders. As we'll see, every WebGL program has to have at least two shaders. In this example, they'll be very simple, but we have to include them. And there'll also be some utilities that we'll routinely include, and they'll all be inside of that HTML file. The JavaScript file will focus on the graphics. It'll be the application and how we want to derive our data, how we put that data onto the graphics processing unit, and then execute that data and do any animation that we want to do. So that'll be sort of the way we'll try to keep things separated throughout the class. Now, if you're running in WebGL, right now WebGL will run in pretty much all of the latest browsers, assuming that the graphics cards that you have will support it, but any recent graphics card should. So Chrome, Firefox, Safari, Opera will work. And recently Microsoft dropped its opposition to WebGL, so you can now run WebGL in the latest versions of Internet Explorer. And the differences among them are very, very minor. I would suggest if you get into a problem with one of the browsers, just try another browser. But generally, I've tested the code at least in Chrome and Firefox and usually Safari, and haven't had any problem. The code is written in JavaScript. The reason being that JavaScript is the language of the web, and WebGL is a JavaScript implementation of a version of OpenGL. Some of you may want to use one of the packages that will convert code, for example, in Java into JavaScript. I don't particularly object to that, but I am not going to, from my perspective, if I have to look at something, it better work, because I'm not familiar with any of those packages. Now, the joy of this is that JavaScript runs within the browser and uses the local resources, and this is a very major issue. Previously, you might have been able to run graphics that somewhere else and display the output on your own system, but that really wasn't using your own local graphics resources, so the best you usually could do was display an image, and that was usually a very slow process of conveying that image across the web from where it was actually running over to your system, plus you had issues with all kinds of system dependencies. The nice thing about WebGL in JavaScript is that because JavaScript runs in the browser, what's going to happen is that even though the code is located on a remote server, that code is going to be run locally within your own browser and use your graphics card and your resources, which are going to lead to very fast implementations and a lot of very nice animations. Okay, here's our little example. Here's just a little snapshot of it. It's just one triangle in red. But you'll see that it has all of the parts you need to in any bigger application. So let's start looking at the code. We'll go through the code fairly quickly, and at the end I'll make a few general comments about JavaScript and the differences between JavaScript and other languages you may be more familiar with. Okay, so let's start with the HTML file. So this is on the website. I think it's under a directory called class, that the same directory you've been looking at on my site, and it's just called triangle.html. So let's look at the code. A lot of this even could be simplified even further, but fundamentally what a web page consists of is a bunch of titles here telling you what kind of resources you need. So this is basically saying, okay, this is an HTML file, and everything until it hits at the end something that's /HTML will be an HTML file. So basically this is saying it's a web page. You can divide the web page up into a number of ways. You can divide it into a head and a body. In fact, that's not for these necessary. If I leave out head and later end of head, won't make any real difference. Okay, so first I have the two required shaders. One is a vertex shader. We'll talk next lecture too about the architecture, but the vertex shader is what manipulates the vertices that your application forms. It's written in the GSL language, and it's a script language. The shaders are actually compiled within the driver for the graphics card. So there's a script tag here. So it's, we have an HTML tag, a head tag. Now we have a script tag that says the ID here, vertex shader, is just allowing you, giving it an identifier that you can then refer to in the JavaScript file. Otherwise, there would be no connection between the two. And it's a type that's recognized because in HTML5 canvas, it recognizes WebGL, and WebGL has shaders in it. So the type X shader X says X-vertex shader says what's following is a vertex shader. Here's the actual code for it. Won't worry too much about it right now. And then something that says that ends that script and says here's the end of that shader. Very, very briefly, this has a very C-like structure. Every shader has to have a main. So here's the main, and this attribute here says that what's coming in from the application is something called position, which is a 4-element vector. We'll see that GLSL supports the basic types you should be familiar with from C, C++, Java, plus some extra matrix vector types, and this is a vector of 4 elements. And now all it's doing is saying the output is the same as the input. So this is known as a pass-through shader that does absolutely nothing. Generally, what the vertex shader will do, among other things, is to do coordinate system conversions that'll convert into the coordinate system that WebGL needs from whatever coordinate system you're using in your application. But since this is a simple application, I gave the data values within as the ones that OpenGL wants, WebGL wants, so I don't have to do any conversion. So all it's doing is passing through the input values out to the output. Okay, next comes a fragment shader. Now what the fragment shader is doing in this case is it's getting all of the interior pixels, which at this point are called fragments, and is coloring them. So its job is to is mainly to produce an output color for every fragment or pixel that comes in. Again, it's a little C-like program. It has to have a main, and all it's doing here is setting the output color to be, this is the red, green, blue, and opacity components. So it's just saying every color that every fragment it gets, it sets its color to be red. So it's a very trivial as we can get shader, but again, both of these shaders are required. Now we'll talk a little bit later about where we can place these shaders. They don't necessarily have to be inside of the HTML file, but it turns out it's at least for now, the easiest, most reliable way to do it is to place them in here within the HTML file. Okay, here's the rest of the HTML file, which really does two things. It brings in a bunch of other files, JavaScript files that we're going to use very quickly. What they are is there's a fairly standard set of WebGL utilities that I think originally came from as part of Chrome, but everybody uses these. I put them in a common directory. They just enable you to set up your canvas very, very easily. Init shaders is a little function we've written that makes it very, very simple to read in and compile your shaders, so you'll always want to use that. mv.js is a little matrix vector package we put together for this class that has a lot of nice little matrix functions that many of which correspond to the older versions of OpenGL, bring back some of the functionality that was deprecated, but is particular to us. You can write your own routines if you like. And finally, we bring in the file, which is the JavaScript file for our triangle function. Notice all of these have script tags because they're all written in JavaScript, and every browser understands JavaScript. And that's the end of the head. And as I said, if you left out the head and the end of head tags, the program would run just fine. But it's nice organizationally for more complex applications to separate them. Here's the body of the program and the end of the body. All the body does is set up a canvas. Now, what a canvas is a surface on which OpenGL or WebGL, and in fact HTML, can draw. It's a particular kind of canvas that supports WebGL. So we're saying, I want a canvas element, and I'm going to give it an ID, again, so that I can refer to it within the JavaScript file, and I give it a height and a width. So very simply what this is doing is it's going to open a window on the screen that has a dimension of 512 by 512 pixels, and it has an identifier called GL canvas, which I'll use in my JavaScript file. If your browser doesn't support HTML5 canvas, then you'll get to the next line and you can't get any further. Again, it's a very simple test to see if your browser supports WebGL. And that's the end. At this point, that's the end of this script, and the action now is going to go on to what's described in these JavaScript files. And the one we really have to look at is triangle.javascript, because that's where we're going to describe our graphics and actually draw something. So let's look at the JavaScript file. Okay. Two things here. Okay, in JavaScript we have variables. We'll talk a little bit more about them later. I really only need two here. I'm going to need a third one a little bit later. I'm going to declare two variables. One is for the canvas, and the other is for some of the data that we're going to form and then send to the GPU. Okay, next. Now over here, what we're going to do is window is the window that we opened in HTML. Window is a global variable known to the system, and all this is saying is window.onload says when everything is loaded in, because JavaScript HTML operates asynchronously. It just goes on loading in the things you tell it to do, and what do you do next? Well, this says when everything is loaded, I want you to run this init function. And what the init function does is set up the canvas. Now what it does is get that element, the one we named GL canvas back in the HTML file, sets it up to be a WebGL canvas using the utility. This is a function in that utility package, which we read in the HTML file. And if we fail to do that, it can't create this GL variable. It'll come back and say there's no WebGL. So once you've done this, you now have an active WebGL canvas. Now we can look at the graphics part. So I'm going to just give you 3 vertices. We're very simple. Again, the coordinate system is rigged. This is it, by default. What WebGL will display is things whose values between -1 and +1. So you can think of that 512 by 512 canvas as corresponding to something that has a lower left-hand corner of -1, -1, and an upper right-hand corner of +1, +1. So here's 3 vertices in it. I'm using the vector2 type, which is defined within our mv.js package, but it's just a little array that contains 3 vertices. Okay, now we get to what's in a way the hard part at first, but it's going to be something we're going to repeat over and over and over again. So let me go through this very quickly and just tell you what the major parts are. So first, we're going to say, how much of that canvas do I want to use? Now remember, I define that as a 512 by 512 canvas, and the viewport is going to say, how much of that do I want to use? And this is just saying I'm using the whole thing. What color am I going to make the background? This is saying I want a red, green, and blue value to be 1. 1 is the maximum. So red is fully on, green is fully on, and blue is fully on. Red, green, and blue add up to white, and so I get a white canvas, and it's opaque. The one here says I want it to be an opaque canvas. Now I load in the shader. So here's the reason that I gave you back in that HTML file this little init shader routine, so we don't have to worry about a lot of little things you have to do. You have to read in your shaders, you have to compile each one, you have to check for errors, and then you have to link the whole thing together. I put all of that into a little program that you can use called init shaders, and just give it. Now these are the names of. This is the canvas, our WebGL context. These are the names we assigned in the HTML file for the vertex shader and the fragment shader. So what will happen is that this will read in those files, it'll compile them, it'll link everything together with the application into something called a program object, which we'll just call program, and then I'm going to use it. One of the things that you can do is you can have multiple programs and swap between them for complex applications. This is a simple one, so we're going to form a single program object once we've initiated our shaders, assuming there's no errors, and then we say this is the program that you should be using. Okay, now next step. What we want to do now is we're going to separate things into 2 parts. One part, and this is the big change in having shader-based graphics. In one part, what we do is we form our data. In the second part, we get that data over to the GPU to be displayed, because the GPU is incredibly efficient at doing that. So rather than define a data point, send it off to be processed, then get another data point, process it, and send it over to display, what we tend to do is form all the data at once, and we'll go over this in more detail, and get that data over to the GPU. So let's see what we have to do that. This says, okay, create a buffer on the GPU, then make that the present buffer. That's what binding does. It makes it the present buffer. And now send those vertices that we had back here. Here were the vertices. Send those vertices over to the GPU. Okay, so that's, allocate a buffer, make it the present buffer, send the data over to the buffer. We'll go over these parameters a little more later, but those 3 steps are what you pretty much always want to do. Okay. Finally, we say, okay, once we put that, now what do we do with that with that data? Well, it's an array, and that array describes positions on the, because that data can describe many things. What we have to do is tell the GPU first the name of the data, which we're calling vPosition. It's the program object that we created in the last slide, and we get that information from the linkage, where that is, what the format of the data. The information is in floats. We don't want it normalized. We'll go again over that. Each data point consists of 2 floats because we're doing a 2-dimensional application, and we're sending it over to there. And we just now have this data array, or let me put it slightly differently. We allocated the array on the GPU. We send data over to there, but we in addition have to somehow tell the GPU what format that data is in and how it couples to our program. And that's what's going on here. Is it's associating variables in the shader. Remember, in the shader we had vPosition, associating that with what we're talking about here in the JavaScript file. And finally, once we've set that all up, now I can render the data. And the rendering is incredibly simple. All we do now is clear the screen. So we clear the color buffer. It's called color buffer bit. It's called our frame buffer. We clear it to the color we set up a few minutes ago, which is white. And then we say draw that data as triangles. Okay, now we put 3 data points on there. So we start at the first one, and I use all 3 of them, and they form a triangle. And that's it. That then gives us our single triangle up on the screen. So you may say, well, there's a lot of overhead going on here, but that overhead of setting up the buffers and describing the data is always going to be the same. It's maybe a little different now, especially for those of you who have done some older OpenGL. This is all sort of new, but once you've done this once, it's going to be the same in every program. For all our data, we want to get it to the GPU, describe what it looks like to the GPU, and then render those data very, very rapidly. Okay. Now, so what I'd like you to do is a little exercise is go run it from the class website and make sure it runs on your browser. Since you can play around with the code, and the code is all script, what you can do is download these 2 files, the HTML file and the JavaScript file, to your own machine. Make sure you can run them from there. Usually what you should be able to do is just click on the HTML file and on your own machine, and it should run. And then try and play with it a little bit. Change the color, add some more data and display some more triangles, move the location of the vertices around, and just convince yourselves that even with this very, very simple program, you can edit it and do some interesting things with it. Go from a triangle to a rectangle. To display a rectangle, you'll note that you have to do 2 triangles to do it, but you'll learn all of this as you go along. But just go and fool around and make sure that you can do that. Okay, so let me finish this lecture up by saying a few things about JavaScript in general. Okay. First, as I said, that JavaScript is the language of the web. All browsers should execute a JavaScript code. It's an interpreted, object-oriented language. Probably the 2 most referenced sources for it in books are Flanagan's book, which I highly recommend. A lot of people really like Crockford's book, JavaScript: The Good Parts, especially if you're a fairly expert programmer. It really does identify there's some really good parts in JavaScript, and there's some really, really poor parts. And as I said, there's a lot of web tutorials out there. If you just go JavaScript tutorial in some search engine, you'll come up with a lot. A couple of notes, things about, because JavaScript generally is not popular in most CS departments, although that's changing very rapidly. The question is, interpreted language, is it slow? Well, yes and no. One thing you'll find if you've used it for a while is that the JavaScript engines in browsers are really, really getting fast, although there's still a fair amount of variability. If you start doing some timing tests different browsers, on different architectures. You get very, very different answers. But what I want to claim is it's not, that doesn't really matter, because the idea of everything we're going to do is to get the GPU to do the work. So the whole job of the JavaScript and the application and all that is to get data over to the GPU and let the GPU do the work. And GPUs are unbelievably fast. They can process tens of millions of triangles per second. So the time you spend up front trying to organize things and getting it out to the GPU often is just irrelevant compared to the size of the problem. So I think, especially for learning, it's not. But even in real applications, and again, if you look at things like Chrome experiments and see some of the really complex things that are done in WebGL, you'll see that JavaScript is really not the issue. JavaScript is it's a very big language, and in a lot of ways it's too big a language in the sense that you can do things in multiple ways in JavaScript, and some of them may not be the best ways to do things. This is especially true if you start worrying about how do you define objects in JavaScript. So what I've done is really tried hard, and I'm really a JavaScript learner, is to find the parts that I need to do graphics reasonably well, and I've carefully picked and chosen the parts that I want. But one of the lessons I learned from my friends that got me to switch over to WebGL, who the deal was I would teach them graphics if they would get me into JavaScript, is to not make the mistake of making my code look like C code, which it used to do, but try and use some of the parts of JavaScript that really do help you clean up your code. And we'll see a lot of that when we start working with arrays very, very shortly. A couple of other notes. JavaScript has very few native types. It has one type of number, which is a 32-bit float. It doesn't have separate integers. It has strings and booleans, but the principal difficulty you could potentially have is with numbers. So x equals 1, an integer isn't really an integer. It's stored as a float. So 1.0 and 1 are really the same. The potential issue, although I haven't run into it very much, is that if you start doing increments and loops and don't have integers, then you worry that, oh geez, round off error going to cause me problems. It can, and you can be a little careful with that in a couple of ways. One of the things that JavaScript has is that it has two equal operators and two inequality operators. Equal means really approximately equal, so you can not worry if you don't have to worry too much about whether things are exact because of the 32-bit float representation. Generally, you use equal just as you would in a Java or C program. If you really want exact equality, then you could always use the equal, and it's probably good depending on whether you're using loops to always use equal and not equal. But as I've said, I haven't had much trouble with that. Another thing about the types is JavaScript is a dynamic language, so you can change types in the course of a program. When you set something to be a number, it can later be a string. It could later be some more complex object. Functions are first-class objects in JavaScript, so a number can all of a sudden be a function. So there are potential issues of it gives you a lot of flexibility, of course, but there are potential issues of sort of losing track of what things are in your program. And that sort of gets tied in with scoping, because scoping is different from the other languages you're probably familiar with. It's called function scope, and so you can actually use a variable before it's been declared within a function, because the variables have scope within that function, and they're said to be hoisted up. That can be good, and it could, until you get used to it, might cause problems. But generally scoping gets to be a problem because you have things that are defined globally, and everything is an object in JavaScript. And so things may be defined outside of anything that you've defined, and there are ways of being careful with that, like always using var to name or declare a variable. But I think you'll get used to that. At least I have. Arrays are one place we're going to have to be careful, and a lot of what you see in people's code will differ if you start looking at WebGL code. So let's start with this, is that JavaScript arrays are not the same as C++ or C or Java arrays. They're not simply strings of integers. They're in fact objects that have methods associated with them. So you can declare an array var a, 1, 2, 3, as we have here, and that sort of looks syntactically like a C or C++ array, but it's not. It has methods associated with it. So there's an a.length, which you can use, which will come out to be 3. It has push and pop methods associated with it, so that you can very easily add or take off elements, and there's a bunch of others to do that. And this is very, very nice. This is how I avoid a lot of loops and a lot of indexing within my applications. The problem comes up where WebGL, because it's a version of OpenGL, really expects very simple C-style arrays to be sent to it. So whenever you send something over to OpenGL, it really wants it to be in the form of a typical simple C-style array, just a string of number, 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 number. So we created a flatten function that if you go back a couple of slides, you'll see in our little program to automatically do that for you. The alternative, which some of the books do and people do, is that JavaScript supports what are called typed arrays that really are like C arrays. And so you can declare a new float 32 array of 3 elements, as we have here, or unsigned integers, 1 byte arrays like that, and use them that way. And these are the kind of things that OpenGL, WebGL wants to see sent over to the GPU. The problem is, if you do that, they are very simple, and you don't get to use all of those methods that are associated with JavaScript arrays. Plus, there's issues of which is the more efficient way to do it. So I found, trying a bunch of these things, that I prefer to work with the JavaScript arrays and then use our flatten function from mv.js to automatically convert things over to float 32 arrays. And if you need to convert to unsigned ints, you can do that. You can do that too. And that, if you go through all our examples, you'll see I've been fairly consistent about that. So finally, I want to make a couple of notes about how minimalist we're being in this course. There's an enormous amount of supporting packages out there for JavaScript and HTML. And I've decided after a lot of experimentation that I really don't want to use anything because I want to focus on the graphics in this course. So I'm not using the standard additional packages that people use. The primary one are CSS, which gives you all the style things. So I won't have things that put borders on my windows and would make blue buttons with little borders around them and nice text, which are very easy to add with CSS. And if you want to do that, go right ahead. On the input side, probably the most popular package is jQuery, which allows you to add the interactive devices very nicely. And that I've decided, no, I'm going to just use the minimal kinds of things to create menus and buttons and sliders, and they're usually just a 1 line or 2 lines of code. If you want to make things look a little more beautiful, then you're certainly welcome to do that. The only caveat I want to give is I'm going to check your code by clicking on your URLs wherever you have your stuff, and it should run within